When artificial neural networks are trained on a sequence of different tasks, they encounter a limitation known as catastrophic interference. This occurs when the model overwrites the synaptic weights that stored its previous knowledge to accommodate new data, effectively erasing what it learned before. Standard regularization techniques like elastic weight consolidation, or EWC, and learning without forgetting, or LWF, attempt to solve this by identifying and protecting important parameters. However, these methods rely on global task boundary information. They require the system to be explicitly notified when one task ends and another begins. These requirements are incompatible with edge-deployed scenarios, such as autonomous sensors or mobile robotics, where task identification is unavailable. Furthermore, these global strategies often require memory budgets that scale upward with the number of tasks, making them unsustainable for hardware with fixed resources. This friction led to the development of TACOS, or Task-Agnostic Continual Learning and Spiking Neural Networks. Spiking neural networks are a class of models that process information via discrete spikes rather than continuous values, mirroring biological neural activity. The core thesis of TACOS is to move the complexity of memory retention away from the network architecture and into the individual synapse. Solving the problem of continual learning requires replacing simple scalar synaptic weights, single numerical values, with a localized, biologically inspired system of multiple variables that protect their own history. To test this localized approach, researchers used the 50-task Domain-IL Omniglot benchmark. Domain-IL stands for Domain Incremental Learning, a scenario where the model must learn new data distributions sequentially without ever being informed of task identities. The constraints were severe, only 75 training images per task, with the network seeing each image only once. This top chart illustrates mean accuracy across 50 tasks. The baseline spiking network, in blue, suffers a steep drop, demonstrating catastrophic forgetting. In contrast, the bottom plot shows TACOS with high metaplasticity, in green, maintaining stable success on task 1 even after 49 subsequent tasks. This level of retention, achieved through local rules without task-identifying information, suggests that the artificial synapse must be reconstructed to function of ERBP, or event-driven random backpropagation, applied to leaky integrate and fire neurons. ERBP is a learning rule that approximates backpropagation by using fixed random weights to communicate error signals. A leaky integrate and fire neuron is a mathematical model that integrates synaptic current over time and fires a spike when a specific threshold is reached. The neuron uses a secondary compartment, labeled U, to integrate error feedback. This compartment accumulates error current until triggering a surrogate gradient update on the synapse. Unconstrained, this new error signal completely overwrites previous synaptic weights. It allows learning but cannot prevent erasure. Surrogate gradients offer the plasticity necessary for spiking neural networks to acquire new information, but they lack the internal stability required for long-term knowledge retention. To add this stability, TACOS introduces metaplasticity, a constraint that regulates how plastic a synapse is at any given time based on its past activity. Every connection in the network maintains its own individual metaplastic limit. The exponential function plotted here governs this limit. As the metaplastic parameter m, or weight w, grows, the output drops toward 0, scaling down incoming weight updates. Increasing this metaplastic state creates a mathematical throttle, making established synapses deeply resistant to sudden modifications. Metaplasticity effectively slows down the process of forgetting. However, it cannot prevent long-term drift entirely if a new task is presented repeatedly over many exposures. While metaplasticity provides short-term resistance, true retention requires a structural anchor to prevent the synaptic weight from drifting permanently away from its learned value. The final structural anchor is synaptic consolidation. This system splits the synapse into two components, an active weight that handles immediate learning, and a hidden, slow-moving reference weight that tracks the consolidated history of the connection. Heterosynaptic decay tethers these weights, creating a rubber band effect. Sporadic errors temporarily displace the active weight, but decay snaps it back to its consolidated position. Permanent learning requires sustained errors, displacing the active weight long enough to drag the reference weight to a new value. This dual weight system inherently filters out transient noise while preserving deeply consolidated knowledge, allowing the network to distinguish between temporary updates and permanent shifts. These mechanisms are unified into equation 11, the single weight update rule that governs TACOS. The first term is the error-driven ERBP update. This is the force of plasticity, pushing the synapse to optimize for the current task. The second term is the heterosynaptic decay. This is the force of stability, pulling the synapse back toward its historical consolidated state. Both of these competing forces are multiplied by the exponential metaplasticity function, which acts as the final throttle on the magnitude of the change. This complex interaction happens entirely locally at the synaptic level. TACOS achieves continual learning without ever needing a global signal to identify the task. Researchers verified these local rules against rate-based algorithms using split MNIST and fashion MNIST benchmarks. These tests deliver classification tasks sequentially to see how much accuracy is retained as the network moves through the data. This table compares mean accuracy across methods. TACOS significantly outperforms models like EWC. Crucially, TACOS maintains a fixed memory overhead that never increases. Analyzing the stability-plasticity trade-off revealed an inflection point in performance. A maximum metaplastic state of 25 was found to be the optimal balance, preserving past knowledge while remaining plastic enough for future learning. By building biological complexity into the synapse itself, the system circumvents the scaling issues inherent in architectural expansion or global task boundary tracking. To confirm the model is behaving according to its mathematical derivation, we can analyze the raw weight change data within the network. This chart shows the plasticity of the input weights. The massive blue bar on the far right demonstrates the volatile weight shifts in the baseline SNN, while the TACOS models on the left show how metaplasticity successfully suppresses those updates. This same suppression holds true deeper in the network at the output layer. The local constraints are actively preventing the drastic weight modifications that cause catastrophic forgetting. Finally, these blue bars show that if local parameters are scaled based on training time, TACOS maintains its accuracy even as dataset sizes vary. This makes it a robust solution for constrained environments. TACOS demonstrates that state-of-the-art continual learning is possible in energy-efficient spiking networks using only local information. The progress of edge-deployed AI depends on engineering synapses that are smart enough to protect their own history, rather than relying on the network to know when the world has changed.